unit, kilonewton meters per meter. We're considering is a 1 meter width strip of the wall. Which we will design, and it will be representative of the whole length of wall. 1 meter width strip of wall. So this dimension here is 1 meter. Because we have these dimensions here, 5 meters, 400 for starters. Class. This is 1,000. It's 5,000. It's 400. So we are considering a 1 meter width strip of the wall. We are only imagining out 1 meter width strip. Okay, so we got a total bending moment value of 522 kilonewton meters per meter. And let's proceed and make a design for this wall. Design. Assume that you're working with mass 30. Use 30 newtons per millimeter squared. Fy 500 newtons per millimeter squared. And the concrete cover is 50 millimeters. Why 50 millimeters? Because this wall is exposed to the ground, and it's basically considered a foundation element. Foundation elements because of the ground conditions that are considered to be more aggressive than if conditions above ground. Then the minimum, I think, from the BS is about 50 millimeters that you can provide for. You can provide for cover. Now, we said that the wall is being pushed. The wall is being pushed that way. some pressure is pushing the wall. We say the wall could fall by, could fail by the stem breaking, the heel breaking, sliding, or toppling as a whole. So we want to check each of these very quickly. We want to check each of these very quickly, just so that you can get a feel of how we would design this wall. So we start with the first possible failure, which is the wall breaking. And I will highlight, I'll highlight for you. Okay, so you know that the wall continues that side that way. Then it does that. It does that. Then it does that. Okay. So we are interested in this area here, which is the base, basically the bottom of the stem. We are interested in that area. That's the area that we want to design for bending. Okay. This area is the one resisting bending. Okay, the bending moment that we've applied. So that's it. So that's what we are checking. That's what we are checking. Checking the capacity of that cross section there against this applied bending moment. So let's say we do the design check. Check BS 8110. Why BS 8110? It's the one that I have the equations of it. The equations in the Eurocode are similar. They have a slight different. I will highlight as we go along the differences. So we start with mu is equal to 0.156 FCU BD squared. Now, this term, just to remind you, because you've done reinforced concrete design, this term here is the internal moment of resistance of the concrete section in compression. If you can remember your reinforced concrete design, you know that for the section, cross section to be adequate or to be adequately designed against bending, you have to satisfy two conditions. The concrete in compression has to be able to resist the applied moment, MA, and the tensile steel, the steel reinforcement steel provided for tension in that section also has to be able to generate a bigger moment than the applied moment. So two conditions. Yes. If you can remember your reinforced concrete. Well, so now with that, we'll come and put in the numbers. Okay, I think the Eurocode, this number here is, this number here I think is 0.167 or something, the Eurocode. You can check. You can check when you find time. Okay. So then the equation, the basic thinking of the equation is, and I could tell you where that difference is coming from, but we will digress too much, and there's no need of digging too much into that. Okay. So therefore, we just write. We just put in the numbers. So therefore, is equal to 0.156 multiplied by, what is our FCU is 30, multiplied by B Now B, so I'm pulling that section, I'm pulling this section here, this section that we have said we are trying to design, and I'm just redrawing it in elevation. So we have a section like that. Redrawing it is elevation. So this is the section that is resisting the bending, and its neutral axis is there. So we've got a neutral axis, okay? And we have the width, which we've said we are considering a 1 meter width strip. So this is 1,000. Right. Say this is 1,000. This is the neutral axis. Sorry, neutral axis. And the depth of this section is 400. Is this number here? 400. So that's the section we're trying to design. Okay. So the B will be 1,000, next 1,000. The D will be 400. Let's try it on that side. D will be 400 minus the cover, which is 50, minus an approximate half diameter of the bar. For example, if we assume we use 20 millimeter diameter bar, so let's say minus 10, half the bar diameter. So this will give us 340 millimeters. It's approximately that. Okay, so we can come here now and put 340 squared. You can be checking this number also from your calculators. So this gives us 541.0 kilonewton meters per meter. Which is greater? Is it greater or lower? It's just about there because we are interested in 522. So it's greater than 522. MA. It's greater than MA. It's greater than MA. MA, which is 522 kilonewton meters. We say therefore, section is adequate. Now, several things that are important, ladies and gentlemen. One, we did mention that generally, as a rule of thumb, the thickness of the stem at the bottom, this value here, should be about 10% of the height of that stem. About 10% of the height of that. So it should have been about 500 millimeters. Thickness of that. Usually, if you follow that rule of thumb, for most applications of retaining of this cantilever retaining walls, you find that it works. You will not have a lot of problems. Now, because we've worked with a slightly smaller stem thickness at the bottom than what would have been agreeable as a rule of thumb, you notice that the applied moment is just about to reach the capacity of the concrete section in compression. It's just about to reach the capacity of concrete section. In fact, if we had used class 25 concrete, so 541 by 25 by 30. If we had used class 25 concrete, the moment of resistance would be about 451, 451, which will be less than the applied moment, and therefore it will not be we can still go ahead and design it as a doubly reinforced section, but it then becomes expensive. It's not economical, it's not efficient in terms of steel reinforcement. So that's why I did mention earlier that as a rule of thumb, you want to start checking your design with about 10% of the height of the stem. So that's the first thing I wanted to mention. Maybe we can write it as a note. As a rule of thumb, stem thickness at the bottom should be approximately 10% of the stem height. In this case, we have assumed 8%, that is 400 millimeters stem thickness against 5,000 millimeter stem height. And it is noticed, it can be noticed, it can be noticed, it can be
方管在那吗？
饭馆不在那儿，饭馆
Yeah.
不在那儿，哪儿？饭馆不在那儿，
Be noticed that the value at the moment of resistance, the moment of resistance is just a bit higher, just a bit higher than the applied moment. If class 25, if FCU 25 newtons per millimeter squared was used, then the MU value would have been exceeded. The MA value. So this generally you want to remember when you go into practice, those who will choose to go into structural engineering, this is important. When you design a cantilever retaining wall, a rule of thumb, if you're not within that range of 10%, you're likely to get into problems that wall. So I go back to a story I told you some time back that this engineer, they didn't check this design. It was suggested by somebody who was not qualified. When it was taken to this engineer, he just stamped it and signed it, and it went to site and it was built. So this wall was 7 meters tall, and the stem thickness at the bottom was 400. Okay, so 7 meters tall wall. Rule of thumb: the thickness of the wall at the bottom, rule of thumb, should have been about 700 millimeters. But what they provided was 400. So 400. So they provided about 57%, 5.7% as opposed to 10% of the thickness. And of course, this wall had a lot of problems. I did mention some of them to you earlier. So this is the first consideration. This is the first thought that I wanted to mention as a side thought at this juncture where we have reached and we have the numbers now. The other thought that I need to raise. Okay, just give me a moment.
一会儿见我的医生。我一会儿见我的医生。我一会儿见我的医生。我见我的医生。最。李老师今天不高兴。
Sorry, ladies and gentlemen. Somebody wanted to ask something. Okay, so this is the first thought. Then you want to ask yourself, so why did we go ahead and try out a 400 millimeter thick wall at the bottom and not a 500 millimeter thick wall? So then I want to now bring to you the other thought about retaining walls. Just confirm. Yeah, that was okay. So I'm sure you've seen in places like on Thika Highway where they've put these cantilever retaining walls. They put these large concrete retaining walls this side and this side of the road, like around the place where they call rosters, where you go up to KBL this side, you come up and you go on to Kasarani this side, and this side is Safari Park. These walls, you notice that they put holes on them, Put holes on them. Those holes are referred to as whip holes. Those walls are referred to as whip holes. Those whip holes, the purpose is to relieve the wall from the water pressure. Let me write that as a second note at this point. Whip holes on the walls are usually installed to relieve the retaining walls of the pressure due to water. The pressure due to water. This effectively kills off, kill is a bad word, removes completely the pressure and by extension and consequently is a better word, and consequently the bending moments resulting from the water pressure. So let's go back and look at the implication in terms of numbers. So the 262.4 is the loading due to pressure. So effectively, if we introduce whip holes onto this wall, just those small holes you see, they put at some intervals. When you drive on along thicker road, you look at the walls, you see they've got about 2-inch wide holes, and they are at intervals. And unless you are looking specifically for them, you will not see them because they are almost unnoticeable. And if you look at those walls, now that this road has been in service for a while, you'll see that actually water does escape through those holes. So you'll see the mark of water that flows down from those walls, and effectively that removes completely this component of the bending moment. And of course the pressure removes and the bending moment also removes. So effectively MA therefore becomes MA is equal to simply these two terms, 102.1 plus 157.5. 157.5. Okay, so we wind up with the bending moment that we need to design for, that is 260 kilonewton meters per meter, as opposed to 522. Now, if you look at this applied bending moment and the value of mu, so mu is much bigger. So this is much smaller than mu, which is 541 kilonewton meters per meter. 541 kilonewton meters per meter. Fellows are talking loudly outside here. Okay. So those are two important thoughts that I wanted to share with you. And that's why at the start I wanted to work with a bigger wall. Then I said, let's work with a smaller one. Because by applying this trick, then you find that the wall already has become very comfortable now. It's important to note that those whip holes have to be well maintained so that we assure that they will continue providing relief to the wall for the life of the wall. Okay, so they have to be properly designed and they have to be properly maintained. If they block, what happens? The pressure grows. We move from 260 back to 522. We move from 260 back to 522. And then if we had designed for only 260, of course the wall will fail because the relief to the wall for a while. Now, maybe you might have considered this in your hydrology training. Effectively, when we put the whip holes, this is what happens. So you've got a wall. Let's say you've got a wall like that. And the retained earth is here. The retained earth is here. Okay, you've got your retained earth there. And the water table is also there. Up there, water table. When you introduce whip holes, sorry. When you introduce whip holes, the water table effectively now forms a curve like that. forms a curve away from the wall. So water table forms a curve due to the introduction of weapons. So the water doesn't push the wall anymore. Now, effectively also, that means that we cannot take advantage of the effective density of the soil, because now the soil is no longer, once we ensure that the water table does not touch the wall, then we have to work with the true density of the soil. And that's why I did not change this density to effective density. Okay, we worked with the true density of the soil, which is 18. If we had worked with the 8, which is 18 less 10, then we would have had to come and back and put back this loading. So these assumptions that I made were because of what I thought we would discuss a bit later. This curve is similar to the curve, they call it the pumping curve of a well. You know, when you dig a well, you're pumping out. The water does it's not a perfect cone linear, it does a curve in towards the well. So as you're pumping, the water table around the well, it does a curve like this. That is a cone. Some of that is curved. You see, it's the same concept. Okay. So now we want to continue with this calculation. Sorry, we want to continue with this calculation. So we have calculated the internal moment of resistance of the concrete in compression. Okay, so we continue with that set of equations from the BS, and we calculate the lever arm. So Z into 0.5 plus root 0.25 minus K, K 0.9. K is MA divided by FCU BD squared, which is now our MA, remember, is this 260, is no longer the 500 something, 522, so it's 260 by 10, 6, FCU 30, B 1000, D 340 squared. To 16, 13, 340. So I'm finding 0.075. So we say therefore C is 340 into 0.5 plus the root, writing this root to kh, the root, sorry, 25 less 0.075, 0.9, to find the number, just shout it out. So, 0.075, 25 answer is that, to answer is that, 1.5, it's 340. I'm finding 308.8 millimeters as the lever arm. Please be checking these numbers so that we be sure we're getting correct numbers. So after that, therefore, we can calculate now the area of reinforcement that is required. Again, this will be MA divided by 0.87 by 500. Let me write the equation first. Fy by Z. I want to talk a bit about this number 0.87. Again, I'm just digressing a bit to give you some thoughts to think about. Now, this is a factor of safety for steel reinforcement to BS 8110, the older one, not the very last one before the Eurocode. So I think this is the BS 8110 of maybe 1985 or something. So later on, the Britons, of course, revised BS 8110 to give us the BS 8110 of 1990 or 1995. And that later version of the BS, they gave this number as 0.95. They gave that number as 0.95. Effectively, what that means, or what that meant, is that they were saying, initially we were putting a factor of safety to say that we are only using 87% of the yield characteristic strength of the steel. But because we have improved a lot in terms of our quality control in manufacturing of reinforcement steel, now we can use up to 95%. It is safe to use 95% of the characteristic strength of the steel that we produce. So that is the Britons. I'm thinking even in the Eurocode, this factor of safety is 0.95. Then we are asking ourselves here, we have some local suppliers of people who manufacture some reinforcement steel, I think like Devki and a few others. Now, recently things have improved significantly, but in addition to that, we produce our own steel, and we have challenges in monitoring. We have challenges in monitoring the quality of all manufactured products that we produce, from food products, medical products, industrial products, etc., etc. We have a big problem, and in as much as we have the CAPES that is supposed to look into that, it is grossly understaffed to be able to effectively do this. And this also goes into building materials as well. In addition to that particular problem, we are importing materials from all over the place. Some places we have absolutely no idea how they control their manufacturing process of steel. So with that, I want to ask a question which you can answer yourselves. You don't need to answer in this class. Would you rather work with 0.87 or 0.95? I choose to work with 0.87 because our system, we have not yet refined our quality control in terms of manufacturing of almost everything to say now we can assume we achieve 95% of the characteristic strength of the yield strength of steel. So that's why I'm putting there 0.87. In the Eurocode, you find 0.95. In the later BS before it became obsolete, it was also 0.95. So I use 0.87. So MA, again, our moment now that we are working with is 260. So we put here 260. We convert it into Newton millimeters. And we put 0.87, 500. Z is 308. Okay, so we calculate that number. 260.87, 500, 308.8 in 1935. 35.6 millimeter squared per meter. Millimeter squared per meter. So this is the reinforcement that we need, minimum reinforcement we need to provide to prevent what? To prevent this wall breaking at this area. Is the minimum reinforcement we need to provide to prevent this wall from breaking at that area, which is our first possible failure mode. If you can remember, first possible failure mode is the stem could break. Sorry, just give me a minute.
And then he that automatically address you for UCS. We give you failure mode in for example, kama ni creative
Yes, Elijah, we can hear you. Elijah. Somebody who is near Elijah to tell him, we can hear them. Okay, great. Sorry about that. There's some gentlemen here who are talking, and it was disturbing a bit my thought process as I tried to teach. So now, we have addressed that possibility there. We have said there's a minimum amount of reinforcement that we need to provide to ensure that the wall does not break at that point at the bottom of the stem, and this is 1935. 1935 millimeters squared per meter. Okay. So you can work with the tables. Those that I have shown a bit of reinforced concrete design, you can also just make this calculation yourself. So if we are working with the class, if we are working with say T25s, we're working with T25s, we say try T25s at 250 centers. This should give us what? 25s times that 1964. 1964. So this is okay. I'm saying try because there would be other checks that we would want to check, and maybe this amount of reinforcement might not be adequate. Okay, for example, for this wall, we need to check the minimum reinforcement requirements. For example, it's just an example. There are a few other checks, but let's say check minimum reinforcement requirements for walls. I think the Eurocode requires that we work with 1%. For walls, the BS requires that we work with 0.4%. So let me check this against 0.4%. Okay. To BS 0.4%. I say please confirm. What I know is that this is true for columns. It's 0.4% minimum, and to the Eurocode is 1% minimum. So it's more than double the minimum. So if we work with 0.4 over 100 times 1,000 times 400, so 1,600. So whatever we provided is it answers the requirement for minimum reinforcement. Okay, so we leave it at that. So now we want to go ahead and check. These are the two possible failure modes. These are the two failure modes. We check the toppling, we check the sliding. Check the toppling and we check the sliding. Let's start with the sliding. Sorry. We do this check and we proceed to something else. You say the force that resists sliding is a frictional force. Between the base of the wall and the soil. Just to remind ourselves, remember, frictional force is given by mu r. The mu from your secondary school physics is the coefficient of friction. It's actually static coefficient of friction. Static coefficient. There is static and dynamic, because even as the wall is sliding, there's still some coefficient, there's still some friction, but that friction is usually a bit lower than the friction that you need to overcome for the wall to start moving. It's referred to as a static friction between base and the soil. And R in this case, of course, we know that this was the reaction, which is a force. So you say in this case, the weight of the wall, the weight of the wall, the base, plus the earth retained above the base. So I draw the wall here. I draw the wall again in elevation. Put our wall. We've got these dimensions for the wall. It's 2,000, 400, 400, 400, and 5,000. So we're interested in these widths. Okay, let's first draw the retained earth here. Retained earth. Retained earth. We're interested in these weights. We've said the stem itself is exerting a weight. The foundation at its center of gravity is exerting a weight. And the retained earth above that foundation is also exerting a weight at its center of gravity. The weight of wall, weight of base, weight of earth. I need more space. Finish this space. What will do? Okay, so that we don't stop this thought process, let's do that. Put a separator here and at least write some of this information on this page. So, weights contributing is a different color. Weights contributing to the reaction are. So weight of wall, 5 meters by 0.4 by 1 meter by the density of to the BS, because to the Euro code it's 25 or 24 and a half, depending on the state of the concrete. So this, we're just using the value to the BS. One. So 5 times 0.4 times 1, that's the volume of that 1 meter strip of stem that you're considering. Then we're multiplying that by the density and we get 48. 48 kilonewtons. And we come to say weight of base. .8 times 0.4 times 1. 2.8 times 0.4 times 1 times 24. Weight of this 2.8 times 4 times 1 times 24. 26.9 kilonewtons. Weight of retained earth. Will be 5 meters from here to there, and 2 meters from there to there, then 1 meter. So 5 by 2 by 1 by the density of soil, which we had written much earlier, assumed to be 18. So 5.2, 5 times 2 times 1 times 18. It's 180 kilonewtons. Okay. So R, therefore, R is 48 plus 26.9 plus 180. This gives us 180 plus 48 plus 26.9, 254.9. 254.9 kilonewtons. Assuming mu is 0.33, so stabilizing force, that's what we call it, stabilizing force against sliding will be mu R should be 0.33 times 254.9 is 84. 81 kilonewtons. Let me see if we can continue. Continue with this calculation on our normal, the usual sketch pattern. Our usual sketch pattern. Yeah. Let's open our usual sketch pattern. Sketch document. Just use it to finish this. So I'm opening that. Please, you'll bear with me. I had underestimated the size of this calculation, so I'll put a line here. Put a line here. I'll put today's date, 16 of 10, 2023. This is our document. We had used it to start off these discussions earlier. So continuation, right here, continuation of wall design. Check. Fork sliding. Okay, and I'll continue in the same color. So we want to calculate now the destabilizing force. Stabilizing force. Destabilizing force. So you got it is the force courtesy of these two loads, courtesy of these two loads, courtesy of the soil and courtesy of the surcharge. You know, because it's a pressure on the wall and it's acting on an area, so we can actually calculate a force for that. So that's the destabilizing force. I am suggesting that we pause here for today and we will continue with this discussion the next session. I want to allow, if somebody has a question or a comment, please you can ask before we wind up this session. Somebody has a question, please you can ask before we wind up.
Excuse me, Prof.
Yes, please.
Would you, since you have calculated for those steel bars, would you please try to indicate their alignment in that retaining wall? So that I can see where they're placed.
What
steel bars.
Yeah, I'll show you. I'll show you where they're supposed to be put.
Okay.
Yeah. Any other question? Yeah, I'll share the notes. Don't worry about that. Okay, so thank you, ladies and gentlemen. Have a good afternoon. We'll meet again the next session and we'll continue with these discussions. Thank you.